Bismillahirrahmanirrahim. Chapter 20, the kinetic theory of gases. Okay, in chapter 18, we discuss the properties of an ideal gas by using macroscopic variables such as pressure, volume and temperature. Okay, such large scale properties can be related to the description of the gas on a microscopic scale, right? Or atomic level or molecules level, where matter is treated as a collection of huge number of molecules rather than a single macroscopic sample. Okay, applying Newton's law of motion in a statistical manner to a collection of particles provides a reasonable description of thermodynamic processes actually. To keep the mathematics relatively simple, we shall consider primarily the behavior of gases, because in gases the interaction between molecules are much weaker in comparison to liquid and solid state. We shall begin our relating pressure and temperature directly to the details of the molecular motion in a sample of gas. Based on these results, we will make predictions of molar specific heat of gases. Some of these predictions will be correct and some will not actually. We will extend our model to explain those values are not predicted correctly by the simpler model. Finally, in this topic, we discuss the distribution of the molecular speed in a gas and apply the results to a liquid. We shall find the concepts discussed in this chapter useful in future when we analyze a situation on a microscopic scale, such as, for example, the analysis of the electrical characteristic of an electron gas in conducting wire. Right, let's begin with subtopic 20.1, molecular model of an ideal gas. Okay, in section 1.2 in physics 1, we introduce a number of types of models. One of it, which is the structural model. A structural model is a theoretical construct designed to represent a system that cannot be observed directly, because whether due to size of it is too large or maybe it's too small, right? An example of a system too small to observe directly is the hydrogen atoms, like this, okay, where it consists of one single proton and one single electron, right? Various structural models of this system has been developed, including the Bohr model. Okay, we will see this more detail in section 41.3. Okay, and the quantum model, okay, in section 41.4. Okay, once a structural model is developed, its assumptions are used to make various predictions for experimental observation of the behavior of the system. Alright, in this chapter, we will consider a structural model for an ideal gas with the goal of relating macroscopic measurement of the gas, which is pressure, volume and temperature, to the behavior of its microscopic components, which is the molecules. The structural model that we will develop is called kinetic theory. This model treats as an ideal gas as a collection of molecules with the following assumption, right? So the first assumption is the physical components. Okay, we consider that the gas consists of number of identical molecules within a cubic container of side length of d, as in this figure. The number of the molecule in the gas is large, and the average separation between them is large compared with their dimension. Therefore, the molecules occupy a negligible volume in the container. This assumption is consistent with the ideal gas model, in which we imagine the molecules to be point-like. To ensure that, this assumption needed because to ensure that, okay, all of these molecules remain as gas. Okay, if they near to each other, they might combine and become liquid. Second assumption is about behavior of the components. Okay, within this assumption, there are three parts. Okay, the first part, okay, the molecules obey Newton's law of motion. Right? Okay, but as a whole, their motion is isotropic. What does that mean? Any molecule can move in any direction with any speed. So they are not related to each other or distinct. The interaction between the molecule, okay, only by short range force, okay, which is near to each other only, right? So that the main behave as an ideal gas, right? No long range force, okay. The molecules makes elastic collision with the wall of the container as well as the neighbors. Okay, elastic collision. Okay, with the wall and the container. Right, so this is the behavior of the components, the second assumption. Okay, although we often picture an ideal gas as consisting of single atoms model as particles, right, just like this, the behavior of the molecular gases approximates that of an ideal gas rather well at low pressure. Okay, usually the internal structure of the molecules has no effect on the motion considered here, right? For our first application of kinetic theory, let us relate the macroscopic variable of pressure to the microscopic quantities. Okay, consider a collection of n molecules of an ideal gas in a container of volume V, alright, as indicated in this assumption number 1. Alright, the container is a cube with the edge of length D. Alright, we shall first focus our attention on one of these molecules of the mass m0 here and assume it is moving so that its component of velocity in the x direction is Vx initial. Right. Okay. The molecules going to make a collision with the wall of the container. Right, like this figure. And bear in mind the collision going to be elastic collision. Why is it must elastic? If it is not inelastic, then might be the molecule going to crumble here and finally become liquid. As the molecule collides elastically with the wall, assumption 2C just now, alright, its velocity components perpendicular to the wall is reversed because the mass of the wall is far greater than the mass of the molecule itself. Right. The molecule is modeled as a non-isolated system for which the impulse from the wall causes a change in the molecule's movement or momentum. Because the momentum of a molecule, the component of it, Px initial, right, is equivalent to m0 Vx initial before the collision. This is the before the collision. This is the after collision, the momentum after the collision. The change in, okay, momentum along x component or direction is equivalent to negative of, this is momentum final minus momentum initial, right? So we will have negative 2m0 Vx From the non-isolated system model for momentum, right, we can apply the impulse momentum theorem, okay, to the molecules to give the F average, okay, on molecules times the delta T of the collision is equivalent to delta P along X or I, which is equivalent to negative 2m naught Vxi. Okay. Where Fi average here is the X component of the average force the wall exerts on the molecule during the collision, and the delta T here is the collision time or duration taken to have this collision happen. For the molecule to make another collision with the same wall after this first collision, it must travel a distance of 2 times T, alright, in the X direction across the cube and back. Okay. Therefore, from the particle under constant velocity model, the time interval between two collisions, alright, is equivalent to the total distance travel over the Vxi. The force that causes the change in the momentum of the molecule in the collision with the wall occurs only during the collision. We can, however, find the long-term average force for many back and forth trips across the cube by averaging the force in equation 20.2. This one, just now. Right. Over the time interval for the molecule to move across the cube and back once. Okay, in this equation. Right. The average change, okay, in momentum per trip for many trips is the same as that for the short duration of the collision. Therefore, we can rewrite equation 20.2, which is this one, as this. Fi average delta T is equivalent to negative 2m naught Vxi, where Fi average bar here is the average force component over the time interval of delta T for the molecule to move across the cube and back. Because exactly one collision occurs with the given wall for such time interval, this result is also the long-term average force on the molecule over long time interval containing any number of multiple of delta T. Now we can do the rearrangement of the this equation, right? Then to have delta T is equivalent to 2D. If we want to substitute our delta T here, okay, from this, right, then you're going to substitute negative 2m naught, okay, Vx initial over the delta T is what? 2D over Vx initial. That is why, okay, you have this pattern. Vx initial going to be squared, and the two constant here cancel out each other. So finally the equation will be left like this. Now, by Newton's third law, the X component of the long-term average force exerted by the molecule on the wall is equals in magnitude and opposite in direction. Okay. So, F on the wall is equal in magnitude but in opposite direction. So, you have the formula of it in terms of this. Right. The total average force, okay, if you want to figure out the total average force exerted by the gas on the wall is found by adding all, okay, by adding the average forces exerted by all the individual molecules striking the wall. Adding terms such as those in this equation for all molecules give us this. Because this constant, so we factorize this outside and representing the number of the molecules. We now impose an additional features from assumption 1 that the number of molecules is large. For a small number of molecules, the actual force on the wall would vary with time. It would be non-zero during the short interval of collision of a molecule with the wall and zero when no molecules happens to be hitting the wall. For a very large number of molecules such as Avogadro number, however, this variation in force are smoothed out so that the average force given above is the same over any time interval. Therefore, the constant F on the wall due to the molecular collision is F equivalent to m naught d summation of Vxi squared from 1 to n, total number of the molecules. To proceed further, let's consider part of the right hand side of the equation just now. Okay. How do we express the average value of the square of the x component of the velocity for n molecules? The traditional average of a set of value is the sum of the values over the number of values. Okay, as we know before. Okay, where this one, okay, now become like this. Isn't it? Just rearrange the n to this side. Using this equation, okay, we substitute this into this equation, right? We're going to have F equivalent to m naught over d n times Vx bar square. Okay, now let's focus again on the one molecule with the velocity of Vxi, Vyi, and Vzi. Okay, the Pythagorean theorem relates the square of the speeds of the molecules to the squares of the velocity component by this method. Right. So hence, from here, okay, the average value of the V bar squared for all the molecules in the container is related to the average value of Vx, Vy, and Vz according to this theory. Because the motion is isotropic, okay, assumption 2a before, okay, the average value of Vx, Vy, Vz square are equals to one another. This one equal to this, equal to one another. Therefore, V bar squared is equivalent to 3 times of Vx bar squared. Hence, the equation just now going to be like this. 1 over 3 and m naught V bar squared over d. This is actually the total force exerted on the wall by all of the molecules. Okay, and we know that the pressure exerted on the wall by the molecules is equivalent to the force applied over the area. The force is this one. The area is t squared. So we can have this method and finally simplify to this. Okay, because d cube is actually volume of the container. Right. Well, finally, okay, we can simplify this term in terms of kinetic energy. Okay, we know that m naught v squared can be some sort of a factor of kinetic energy if we multiply by half. So if we want to multiply this by half, this one also must be multiplied by 2 so that cancel out each other. So we can have the pattern of the formula in terms of this. Pressure is equivalent to 2 over 3 n number of molecules over the volume times with the half m naught v bar squared, where half m naught v bar squared is actually kinetic energy of the gas. We can gain some insight into the meaning of temperature by first writing equation 20.15 in the form of this just now, right? To relate it into equation of states for an ideal gas, which is PV equivalent to NKBT from chapter 18. Okay, so now if we rearrange this and equate this with NKBT, so you have this method where the n can be cancelled out. So from here, if let's say we want to have focus on the temperature, then you may rearrange the KB to this side. So you will have temperature is equivalent to 2 over 3 KB times half m naught v squared bar, right? This result tells us that temperature is a direct measure to the kinetic energy of the gas. In chapter 18, previously, we could only define temperature macroscopically in terms of transfer of energy between two objects. Okay, in this equation, right, we have deeper definition of temperature in terms of the macroscopic motion, okay, of the molecules of a substance, right? By rearranging this equation, we also may have in terms of this half m naught v bar squared equivalent 3 over 2 kBT. So what we have here, this is actually average kinetic energy per molecules, right? Where kinetic energy is directly proportional to the temperature. This equation shows us that the average translational kinetic energy, okay, per molecule is 3 over 2 kBT because Vx bar squared is equivalent to 1 over 3 V bar squared. It follows that, okay, half m naught V bar squared, okay, is equivalent to half kBT. In similar manner, for the y and the z components or direction, half m naught Vy bar squared is equivalent to half kBT and half m naught Vz bar squared is equivalent to half kBT as well. Therefore, each of the translational degree of freedom, okay, contributes an equal amount of energy, which is half kBT, right, to the gas. In general, a degree of freedom refers to an independent means by which a molecule can possess energy. A generalization of this result known as the theorem of equipartition of energy. What is the theorem said? It says each degree of freedom contributes half kBT to the energy of a system, where possible degrees of freedom are those associated with translation, rotation, and vibration of molecules. The total kinetic energy translational can be figured out by multiplying half m naught v bar squared with the number of the molecule exists for that system. Okay, which gives us 3 over 2 n kBt equivalent to 3 over 2 nRT. By make use Kb, Boltzmann constant, is equivalent to R over Na, and N equivalent to small n number of mole times Na. This equation represent the internal energy of the gas. This result implies that the internal energy of the gas depends only on the temperature. The square root of the V bar square, right, is called the root mean square speed. RMS here stand for root mean square speed of the molecules. From equation 20.19, which is half m naught v bar squared is equivalent to 3 over 2 kBt. From this equation, right, we find that the RMS speed, okay, which is this one, square root of this one, is equivalent to, if you want to square root both sides, isn't it? That is how we figure out this, equivalent to 3 kBt over m naught, because the half cancel out already. Okay, we also can substitute 3 kBt over m naught with the 3RT over m, where m is m naught times Na. Okay, and R is related to Na by this. R is equivalent to Kb times Na. So then, what is m? Is molar mass. What is m naught? Is mass of the substance. Right. You may refer to this table, okay, where it gives us information of the molar mass and also the RMS, VRMS, for many types of gases. Example 20.1, a tank of helium. A tank used for filling helium balloons has a volume of 0.3 meters cubed and contains 2 mole of helium gas at 20 degrees Celsius. Assume the helium behave like an ideal gas. A. What is the total translational kinetic energy of the gas molecules? So, E internal now is equivalent to kinetic energy total in terms of translational motion, equivalent to 3 over 2 nRT. So, this is the R, this is the T in Kelvin, and the N is not written here, so madam add up here 2. So the final answer should be 7.3 times 10 to the power of 3 joules. What is the average kinetic energy per molecule? So average kinetic energy is half m naught v bar squared, equivalent to 3 over 2 kBt. Right? In comparison to this is equivalent to 3 over 2 nRT. Right? So this one 3 over 2 kBt. So you will get this equivalent to 6.07 times 10 to the power of negative 21 joules. Make sure the T is in Kelvin because your Kb unit is joule per Kelvin. Right? Then, what if the temperature is raised from 20 degrees Celsius to 40 degrees Celsius? Because 40 is twice as large as 20, is the total translational energy of the molecules of the gas twice as large at the higher temperature. So, the expression for the total translational kinetic energy, which is, just now we have K total translational equivalent to 3 over 2 nRT. Okay, due to this, alright, depends on the temperature, as we know. This is the one that varied. Okay, and the value for the temperature must be in Kelvin, as Madam stressed just now, not in degree. Okay, therefore, the ratio of 40 to 20, if you want to put 40 ratio to 20, okay, is not appropriate, cannot be used, right? Because the temperature must be in Kelvin, right? So the ratio of temperature in Kelvin for 40 degrees Celsius to 20 degrees Celsius is 1.07. So it's actually not going to be doubled or twice